Okay guys, good morning. Today I would like to do a quick review of chi-square goodness of fit and then teach you about two other chi-square tests. The first is the chi-square test for association, and the other one is chi-square test for homogeneity of proportion. So before I can do those two, let's do a review of chi-square goodness of fit. Let's go to page 5. Page 5 says airbags in cars have become an increasingly important safety feature to consumers. It has been stated that 45% of non-domestic cars are equipped with a driver's side airbag. 15% with both a driver's side and passenger side airbag. It's 2 airbags. And 40% with no airbags. A random sample of 48 domestic cars was obtained and the airbag status for each was recorded. The results follow. Okay, so let's begin this. No airbags, 1 airbag, 2 airbags total. And they gave you observed counts. These were given 16, 23, 9, a total of 48. And you want to test the following hypothesis. H naught, probability of 0 airbags is 40%. Probability 1 airbag is 45%. And probability 2 airbags is 15%. All these have to add up to 1, which they do. Versus HA, the distribution is different than stated above. So it's my job to find the expected count, expectation. So mu equals n times pi. So n is 48. So 48 times 0.4 gives me 19.2. 48 times 0.45 gives me 21.6. And 48 times 0.15 gives me 7.2. Do not drop any decimals. Keep all the decimals. And the total again, of course, is 48. So my chi-square test statistic, chi naught squared, is summation observed minus expected square over expected. So this is observed, this is expected. So 16 minus 19.2 squared over 19.2 plus 23 minus 21.6 squared over 21.6 plus 9 minus 7.2 squared over 7.2. When I add all these up, I get 10.24 over 19.2 plus 1.96 over 21.6 plus 3.24 over 7.2, giving me 1.074. That's the chi naught squared test statistic. And then I go to my chi-square table with k minus 1 degrees of freedom, where k is the number of categories. So I have 3 categories: You want to be careful that you don't say 1, 2, 3, 4, right? You don't include the total, obviously. So I have only 3 categories. So this would be done chi-square 2 degrees of freedom. So let's go to our chi-square table. And I don't think they gave us any alpha level, right? No alpha level provided in this problem, so let's use 0.05. Since no alpha was provided. So let's go to 0.05 and 2 degrees of freedom. 5.99. 5.991 is the critical value. And I go and I drop my 1.074 into this picture. This is 0 for chi-square. Go and drop this number and this is what I get. 1.074 does not fall in the critical region. Therefore, do not reject H0. The test is not significant. So there is insufficient evidence that the probabilities are different than those stated in the null. Basically, this is saying that there's a good fit. Follow me? A large chi-square value would mean, a value in here would mean that it's not this distribution. The distribution is different than the one stated over there. This one is saying, I have no evidence that the distribution is different than that distribution. Are you with me? So that's chi-square goodness of fit. It's performed at k-1 degrees of freedom, where there are k categories. Is it totally clear? Great. Let's go to the next chi-square test. Oh, by the way, can we do p-value for this before I move on? How about p-value? P-value is chi-square CDF 1.074 comma infinity comma degrees of freedom. So p-value equals chi-square CDF of chi-naught squared comma infinity comma degrees of freedom. So it should be some huge p-value. What do you get when you do that? Let's see. Stat, test, chi-square, no stat test, no. Second distribution, chi-square CDF of 1.074 comma 100 comma 2. 0.58. 0.58 is the p-value. So p equals 0.58 and alpha is equal to 0.05, p greater than alpha. Do not reject H0. Just like that. Okay. So let me go to a different test, chi-square test of independence. And let's see where that is. The very next page, page 6. Chi-square test of independence. So again, for this test, you're talking about one sample from one population. So a single sample is taken from the given population, and you're looking to see, want to see if there is association between the row and column variables. For example, perhaps I want to see if eye color is associated with hair color. Meaning, do blondes have blue eyes like that? What do you think? We'll see. We'll find out. So H naught in this case would be there exists. This backwards E means there exists no association. Meaning independence. Meaning there is independence between the row and column variables. And HA says there exists an association between row and column variables. The requirements for the use of this chi-square is that all expected counts be greater than or equal to 5, or 80% of expected counts be greater than or equal to 5, and all of them greater than or equal. This test is done at R minus 1 times C minus 1 degrees of freedom. I'll explain that in a second. Where you have a matrix of R rows and C columns. So let's say I have on page 9 a problem that I would like to do. It says a public opinion poll surveyed a simple random sample of 1,000 voters. So this total right here is 1,000. Respondents were classified by gender and by voting preference. Republican, Democrat, Independent. Results are shown in the table below. Is there a gender gap? Meaning, do the men's voting preferences differ significantly from women's voting preferences? Use a 5% level of significance. So this is a 2 by 3 matrix. 2 rows, 3 columns.